Now we moved on to the new topic, which is called as shock wave. Okay, so you have like if you drop something soft, okay, or like if you have a pond of water and if you throw a stone into it, what will happen? It will create waves, right? It will be created from which point? Where you drop the stone, right? But it will be only there? No. It passes like this, right? Okay. You drop something in water, okay, it has a ripple, they call it the ripple effect. Okay. So the water is not only disturbed at this point, it is disturbed at other points as well, right? And this is what we call as a wave. Okay. The same thing which you see in the sea, in the ocean. Okay. Nothing is happening where you are standing, right? But the waves are coming or not. Okay. I am just standing there. Okay. Am I creating the waves? No. Are you doing something to create the waves? No. Waves are created from where? From the ocean. But are they just there? No. They come to the end, right? They come to the shore where you are standing. Okay. So the same happens when you create any disturbance in traffic. Okay. Waves are created. When there is any disturbance in traffic flow, waves are created. Okay. The disturbance is called as a shock, and the effect of the disturbance is called as the wave. Okay. The shock is the disturbance we are creating, and wave is the effect of the disturbance. Clear? Okay. Before we move on, we will see it later on as well. Some disturbances are good, some are bad, right? Disturbance can be good, but can be bad. Like one of you starts sleeping, and I wake him up. I have to disturb them. If I don't disturb, they will keep on sleeping. Huh? So that is good or bad? Bad, huh? Good for me. Okay? Better, okay. So, same happens in traffic. Some shock waves are negative, some are positive. Okay, some are negative, some are positive. So, how do we disturb the traffic flow? We disturb the traffic flow with a sudden increase or decrease in capacity. Okay, whenever traffic flow meets a sudden increase or decrease in capacity, a shock wave is created. Okay, so the disturbance is a sudden increase or decrease in capacity. Okay, and this often happens at a point which we call as a bottleneck. Okay, now this one, the bottleneck is mainly associated with decrease in capacity. Okay, a bottleneck is usually a point where traffic capacity decreases. Okay, so shock wave normally happens because of decrease in capacity. Okay, and the point at which this happens, we call this point as what? A bottleneck. Okay. Now, where a bottleneck is created or by which reasons a bottleneck can be created? It can be created because of a crash. So we are now, even if you look at the first example, now you can imagine that when I say decrease in capacity, I am not only talking about design capacity. It can be some temporary disturbance as well, like a crash. An accident happened, 2 lanes are blocked. Did I change the design of the road? No. It's a temporary blockage. But this blockage is also causing decrease in capacity. Okay. So decrease in capacity can be temporary or it can be by design. Okay. So a crash. Now this is by design, right? You design number of lanes, 2, 3. Okay. So it was 2 now. Now it is 1. Again decrease in capacity, right? Okay. restricted bridge sizes. So you are on the highway was very wide. Now you came on the bridge is narrow because they cannot make it so wide as a road itself. Work zone, construction work is happening beside the road. Some maintenance work is going on the road. Okay, so that is called as the work zone. A signal turning red. Routine, right? Happens very often. Come to signal turns red. Red means what? Capacity became what? When signal became red, capacity became 0. You cannot move, right? 0. So, and other things like this. Okay, so some of them are temporary, some of them are permanent. Okay, by design. Okay, so you can see this graph which I showed you earlier. This is between density and flow. Okay, so you can see this is between the two segments. Okay, you see two curves here, they are between the two segments. Okay, this point, the maximum point of flow, what do we call it? Capacity. Okay, so you can see capacity of this curve is higher, capacity of this curve is lower. So this is, let's say, segment A, higher capacity, segment B, lower capacity. Okay, so what normally happens? You are on the first segment. Okay, the flow on the first segment is, let's say, this much, Q1. Okay, on segment A the flow is Q1, the density is K1. Now this flow, it tries to go into segment B. Segment B has low capacity. Now you can see Q1 is more than the capacity of the second curve, right? Okay, so Q1 cannot enter here, right? The whole Q1 cannot enter here. How much will enter? Only up to Q2. Okay, and what is Q2 for curve 2? What is this value? No. What is Q2 for this curve? Which flow is this for this curve? Capacity, maximum flow, right? Okay, so out of Q1, only Q2 can enter here. So that means what? This difference will go where? Cars were coming, right? 1,000 cars were coming. Only 700 passed from the next segment. The remaining 300 went where? On your right there. They went where? What will happen to these 300 cars? The cars which could not pass from segment B, what will happen to them? They will stop, right? They will start a queue. They will start a queue. So whatever is the difference between these two, it will start a queue. Got it? Okay. Now you can see here when it was Q1, the density was K1. In segment A, the set density was K1. In segment B, the flow became Q2, okay, and the density became K0. Now which one is higher, K1 or K0? K0 is higher, right? So density is now more congested. Okay, the density is now density is higher, means less spacing. Okay, so segment B created a shock wave. Capacity reduced, shock wave created. When shock wave created, they are the queue now. Okay, so there are vehicles in the queue, and the vehicles which are moving forward, they are not moving with high speed. Okay, so high density means low speed. Now your spacing is less, right? The speed will be lower. Alright? So these are all the effects of the shock wave. Okay. So now this Q, so there is a segment B which has low capacity. After segment B, there is another segment C, which is back to normal capacity. Okay, so there is segment A then B, then C. Okay. So this one has C1, which is more than C2. Okay. And this one again has C1. So back to the first curve. Back to this one. Okay. Now what will happen? How much flow is passing from segment B? This much, right? So this flow will go here. Okay. It will not go here because this is the congested part. We do not. This will happen when you cross the capacity of segment B. Do you cross the capacity of segment B? No. My flow is only this much, right? Okay. So the flow which is passing into segment C is only this much. Okay. So now, because the flow is only this much, the density is K3 now. Okay. So earlier in segment A it was Q1, K1. It passed to segment 2, it became Q2, capacity of segment 2, lower value, density K0, which is higher. Okay. So they are passing from a congested segment now. Then this small flow reaches the next segment, which is bigger. Okay. So now they are, you can see the density has improved. Density reduced means improved, right? Less density is good. More spacing. Got it? Okay. So when Q2 reaches the next segment, density reduces. Okay. Because they have more space, less flow. Remember the example I gave you? These are 1000, these are only 700. Okay. So now instead of 1000, 700 are passing to the next segment. Okay. Which has more space. Okay. So that's why their density improved. Got it? Clear? Okay. Now the normal case is, the easier case is, you have flow Q3 passing from segment A. Okay, it is below the capacity of segment A, no problem. Okay, it is also below the capacity of segment B, so no problem. It will pass from A to B and to C, no problem. Okay, the flow will not change because none of the capacity is breached. Okay, but what will change? Then there is something which will change. It's shown in this graph. Density will change. Okay, the segment B can handle this flow, but it has still less width, maybe less lanes. Okay, so it will still create a small shock wave with higher density. Okay, so you can see there Q3 density K3, Q3 density K3B. Okay, the density has increased. Density increase means speed decrease. Alright? Okay? Clear now? Okay. So even when you don't have the Q and all these shock waves and so on, you can still have the reduction in speed and so on. Okay. Now okay, if you take, so this is flow and density. Flow and density. Okay. The equation of traffic flow is flow equals density into speed. Okay, flow equals density into speed. So the speed equals flow upon density. Okay. So if I take the slope at any point, it will give me what? Speed. Clear? Okay. This is when I take the slope at the same curve. So I take the slope of this curve, it will give me speed at this point, speed at this point, speed at this point, speed at this point. Got it? Okay. Now, if I take the slope between these 2 points, this is a slope, right? It was Q1, it became Q2, right? If I take the slope between these 2 points, it will be a speed, right? Because slope means what? Flow upon density. Flow upon density is what? The speed. but because I am taking the slope between 2 points, 2 different curves now, it will not be the speed of flow. It will be the speed of shock wave. Okay, now what is the meaning of the speed of shock wave? We said when this happens, there will be a Q, right? There will be a Q. Okay? When shock wave happens, a very important point for us is how fast the Q will expand. Okay? So if the shock wave is there for 1 hour, how many vehicles can I expect in the Q? How long will be the Q? How much space I will need for the Q? Okay? So this is why I need the speed of the shock wave. Okay? Got it? So on the flow density curve, if you take the slope, it will give you speed. If you take the slope on the same curve, it will give you speed of the flow. If you take the slope between 2 different curves, it will give you speed of the shock wave. And this speed will tell you how much space the shock wave will grab on the road after some time. Okay, that's the same units as speed, miles per hour. If the shock wave is for 1 hour, it will catch this much space of the road, miles. Sorry? Clear? Any questions? Okay. So we have different types of shock wave, like I said. Some of them are positive, some of them are negative. So we have frontal stationary shock wave. Okay. The stationary means what? At rest, right? Stop. Okay. So when do cars completely stop on the road? Red light. Now you get me. It happens from the front, right? So I come at some line, stop line, signal is red. I will become what? Stationary. Okay. And this starts happening from the front, right? The first car will stop first, then the next, right? So frontal stationary. Clear? The shock wave which happens in which cars stop because something in front of them. That is called as frontal stationary. Okay. It can happen because of signal, or it can happen because of a serious incident. Something happened which is completely blocking the house, the entire light. Okay. So it happens as a stop line. Okay. Then we have backward forming. Okay. So this is when capacity is reduced. The case which I was showing you in the graph. This one. Did the flow completely stop? In this case, did the flow completely stop? No, right? It was moving with less speed with the Q, but it was moving. Okay. So that is a reduction in capacity, not becoming zero, but a reduction. So not a stationary. It is not stationary. Okay. So capacity reduced, and you have why we are calling it backward forming then. What is forming? In the last example, what was forming here? Q. So forming means a Q. Okay. And the shock wave continues. The Q will extend back, right? So now the Q is only 10 vehicles. After 15 minutes, it will be 15 vehicles. After half an hour, it will be 50 vehicles. Okay. So these vehicles are increasing in which direction? Back, right? Or downward? Okay. So that's why backward forming. Backward forming. Okay. Okay. So not stationary, but then the Q happening and backward. Okay. And this backward direction is called as upstream. Upstream means backward. Okay. And the point where it usually happens. Okay. How did we define a bottleneck? A point where yes, reducing capacity. Okay, clear or not? Okay, and this can happen when the number of lanes are reduced, or some lanes are blocked or closed because of some work or accident or something. Okay, so I told you some shock waves are positive as well, right? But positive comes after negative. Positive comes after negative. Okay, remember this for life. Positive comes after negative. So after my class, you can relax. Positive comes after negative, right? And you can see well. Okay. But this is called as backward recovery. So we are recovering from the shock wave. We are recovering from the Q. So when the shock wave happened, the previous one, backward forming, so the Q was forming, right? Now the Q is recovering, meaning it is reducing. The Q is reducing. Why it is reducing? That's why we call it backward recovery. It is reducing because the demand has stopped or decreased. Okay? So the vehicles were coming at 1,000 every hour. The Q was increasing. Okay? It was happening in the morning, let's say. Okay? But after 9 o'clock, office time is over, school time is over. So now the people who are coming to the queue are becoming less and less. Right or right? Now they are not 1,000, they are only 400 per hour. So this will start reducing the queue, right? Because the same number of vehicles are going forward, but the number of new vehicles which are coming are less. Okay, so the queue will start reducing. But the queue is not reducing because something happened at the front. Queue is reducing because people at the back are reducing. Right or right? So that's why that's called as backward recovery. It is recovering from the back. It is recovering because less people on the back. Okay? So, and this can happen when you have what? I believe the examples are not correct. Signal that approach or certain change from left to green. I need to change the example. This does not go with the definition. I believe I just copied it twice in the two slides. Okay, so now then we have real stationary and forward recovery shock waves. Okay, when demand, so this happens when the demand flow rate, so they happen together in pairs, and it happens when the demand was high. Okay, first of all it was high, so it was more than the capacity of the bottleneck. Okay, it created the shock wave. Okay, and the demand, then the demand flow rate reduces to the capacity of the bottleneck. So it did not go below still. Okay, so that's why real stationary. Okay, real stationary. And forward recovery. Okay, because now you are recovering from the front. Okay, you will recover from the front. At the back you will still have the Q, but the Q will be of the same length. Okay, what is happening? Demand was 1,000. Capacity was 800. Q is 200. The Q is 200. Okay, and this is the Q. Okay, then the demand reduced to 800. 800 only. Okay, not less than that. Only 800. Okay, the capacity is also 800. Demand is also 800. Okay, so 800 are coming, and only 800 can leave. Remember, there is a Q, right? The Q is still there. Okay, the Q will recover when the demand goes below 800. Okay, so that's why rear stationary. The Q which was at the back will remain. Like the length of the Q. The length of the Q at the back still remain. Okay, but forward recovery, meaning it will not expand. That's forward recovery. Okay, so these two happen together, or these two are like one started because the demand was more than capacity. Okay. Then Q became stationary because the demand and capacity became equal. Right. Okay, let me just check one thing. When the demand becomes less than capacity. Okay, yes, okay. So, yeah, I forgot this point and the example fits here. I was thinking that we have another type of, I keep on forgetting the types, like how many are. Anyways, so backward recovery happens when the Q starts reducing from the back. Okay, it can happen, or length of the Q starts to reduce. It can happen when the demand decreases. The demand was 1000, now it is only 400. I gave the example of morning. Okay, so when the demand from the back is less, the Q will start reducing, right? Okay, and Q will also start reducing if you remove the restriction from the front. Okay, so the signal was red, now it has become green. So restriction has gone, right? Okay, so the people start moving, and when they will move, after some time the Q will be gone. Okay, so backward recovery can happen in both ways. Either, but backward recovery basically means the Q reduces. The Q can reduce because the demand at the back has reduced, and the Q will also reduce if you remove the restriction from the front. Okay, so in both cases we call it backward recovery. Okay, and this is where the Q is constant. Okay, but the Q constant means the Q has first happened, right? Okay, and so on. Okay, so this is like a tunnel. So before and after the tunnel, you see 4 lanes, right, in each direction. And inside the tunnel, there are 2 lanes. So you can see, what do we call this? Bottleneck. Okay, and this bottleneck will create a shock wave, which they are trying to show here. Okay, when we will enter from here, we will have a backward forming shock wave, right? Not backward stationary. Sorry, frontal stationary. Frontal stationary cannot happen, right? Flow is moving, right? So backward forming. Okay, then it can be rear stationary. When will we reach this one? Rear stationary. Q is constant, and Q becomes constant when what happens with the demand? Demand decreases to what? Equal to capacity of the bottle. Okay, so these are different times. So when demand was higher, we had backward forming. Demand reduced to capacity, we have what do you call rear stationary. Okay, and then we have forward recovery. Okay, so forward recovery is when you are passing through the tunnel, when you go to the other side, that is forward recovery. Okay, now you move at more speed, right? Move at more speed. You are in 2 lanes, now you are 4 lanes, right? Move at more speed. So this is for this direction, and this is a mirror image on this direction. Got it? Mirror image. Okay, so I told you for us, the length of the shock wave, the length of the Q is very important, and the length depends upon the speed of the shock wave. Okay, speed of the shock wave. So how do we calculate the speed of the shock wave? 2 segments, P and Q. The flow is going in segment P with a speed of U and density of K. Okay, and flow equals what? Keep this in mind. Okay, they are giving the speed and density. I will multiply them, I can get. Okay, so when this will reach in segment Q, okay, segment Q is shorter. You can see they made it shorter as well. So that means the speed will reduce and the density will increase. Okay, so K2 and U. Okay, and this is a separation line between the 2 segments. Okay, now if a shock wave happens, shock wave will start from here, right? If a shock wave happens, to start from here, right? When you are trying to enter the new segment. Okay, so this is the point of start of the shock wave. Clear now? Okay. So, so there are two speeds. In each segment there are two speeds. One is the speed of the flow, the other one is the speed of the shock wave. I told you here, if you just take the slope like this, speed of the flow. If you take the slope between these 2 points, different curves, this is the speed of the shock wave. Got it? Okay. So if you take the difference of speed of the flow and speed of the shock wave, speed of the flow, speed of the shock wave, you call it relative speed. Okay, relative speed. Relative speed is the difference between speed of the flow and speed of the shock wave. So how quickly the flow is moving and how quickly the shock wave is forming. How quickly the Q is forming. Okay. If density is K1, speed is U1, you multiply them, you get flow Q1. If it is K2, U2, multiply them, you get Q2. So this is for this segment, this is for this segment. So I know the flow in both of them because I know the density and speed. Okay. So I told you in both segments we have relative speed, right? So this is the relative speed for this segment. Okay. Any problem up to here? Okay. Now, number of vehicles which will pass from segment 1 to segment 2. Okay. The units of flow are vehicles per time. This is flow. And flow equals to what? Okay? Speed into density. So this will give me vehicles upon time. If I multiply this with T, this will become what? Got it? So this is how they are calculating number of vehicles. Flow into time. Okay, but because there is a shock wave, okay, so the complete flow is not going in segment 2, right? There is a shock wave here, so Q1 is not going in segment 2. So I cannot, if I do U1 into K1, what will I get? Q1, which is a full flow. But in the shock wave, the full flow cannot enter there, the Q. Got it? So that's why we are using relative velocity, not the velocity of the flow, the relative velocity. Okay? So the flow is trying to move and the shock wave is happening. And whatever is the difference between them, those are the vehicles which will move forward. Okay? So, number of vehicles which are passing from segment 1 and number of vehicles which are going in segment 2. So in segment 2, this will all become 2, right? In the same time. In the same time. Time will remain the same. I am trying to calculate how many vehicles are going from segment P into segment Q at the same time. So the number of vehicles going from segment P are the same which are going in segment Q, right? They are same. Okay? So N1 and N2 should be equal because T is same. Okay? So I have N1, I have N2, I put them equal. Okay? N1 equals to this, N2 equals to this. Okay? So it was, I write a step here, UR1 K1 T, UR2 K2 T. Okay? What was relative velocity? The difference of flow, speed and shock wave speed. So K1 T. And this one is U2 minus UW K2. Okay? This is what you see here. UR1, UR2. Okay? Now in this equation you can see T was common on both sides. So T is cancelled out. You don't see T here. Okay. Then I'm trying to calculate what? Speed of the shock wave. So I'll put UW on one side, everything else on the other side. Okay. Okay. So what did you get in the end? These are the steps, you can have a look at it. But this is the equation. U1, UW on one side, everything else on the other side. Clear or not? Where Q1 and Q2, initial flow, final flow. Initial, final. And K1 and K2 is what? Which density? Initial, final. Got it? Now you look at the final thing, then we will close for today. You see here shock wave. Okay. What is the normal direction of the speed? Forward, backward. Speed, normal. Forward or backward? Forward, right? Okay. Shock wave. Forward, backward. In this case, backward. Q is pointing backward. Okay. So this, I will get this value negative. Unless it is a recovery. I told you, right? There are two. There is positive, there is negative. Okay. So, unless it is a recovery, we will get this one. The negative is wrong. The point is negative is wrong. Because we are talking about speed and shock wave, which is a Q. And the Q does not happen forward. Q happens back. Clear or not? Any questions? Okay. Now, important two things. First of all,